All right, today we're going to tear down an electric vehicle's powertrain, but not with a wrench. We're going to look at it from an engineer's perspective and explore the incredibly complex balancing act that's required to make everything work together in, well, high-performance harmony. You know, we all see the flashy marketing numbers, 0 to 60, total range, crazy horsepower figures. But let's get real. How do you actually engineer a system that delivers all that, day in and day out, without falling apart? It's so much more than just slapping a giant battery and a powerful motor together. It is a constant, delicate dance. So to really get it, we have to follow the path of the energy. It all kicks off in the battery. Now, the battery itself is this amazing piece of chemistry, constantly juggling raw power for that instant acceleration against energy density for long-range driving. That power then flows through something called the DC link to the inverter, which is kind of the digital brain of this whole operation. The inverter then chops up that power and feeds it to the motor, which has the tough job of turning electricity into motion while fighting off heat and inefficiency. And finally, you've got the gearbox, which multiplies that force to get the wheels turning. Here's the key. Every single step in this chain is a world of trade-offs. A decision you make right here has consequences all the way down the line. So let's start at the source. Now, you might think the story starts with the battery cells themselves, but honestly, some of the trickiest engineering challenges are hidden in just getting that power out of the battery cleanly and delivering it to the rest of the car. Okay, so think of the DC link as the powertrain's superhighway for high-voltage electricity. And it's not just some simple wire, okay? We're talking massive copper bus bars to handle huge currents and special capacitors that act like shock absorbers for the flow of that electricity. Because if that highway isn't perfectly smooth, you're going to get chaos downstream. So what happens when things aren't in tune? This isn't just a hypothetical. It's a make or break engineering problem. What happens when the natural hum of your power source clashes with the operating rhythm of the device controlling it? You get something called electrical resonance, and it is bad news. It's exactly like hitting the perfect musical note to make a wine glass vibrate itself to pieces. In an EV, the DC link capacitor and the battery's own internal physics can create a circuit that just loves to ring at a specific frequency. And if the inverter happens to be switching at that same frequency, boom, the voltage can go wild, creating huge spikes, instability, and it can literally destroy expensive components. Engineers have to work really hard to design around this invisible landmine. All right, let's move on to the heart of the system, the inverter. Now, its job sounds pretty simple, right? Just turn DC from the battery into AC for the motor. But the reality is anything but simple. The inverter is basically the ultimate power choreographer. It takes the steady, boring stream of DC voltage and, using a bunch of ridiculously fast switches, it sculpts a perfect, variable AC waveform. This is what tells the motor exactly how fast to spin and with exactly how much torque. It's an artist. So how does it do the sculpting? It uses a clever trick called pulse width modulation, or PWM. Just imagine you have a light switch. To make the light dimmer, you could just flick that switch on and off, so fast that your eye just sees a dimmer, steady light. That is PWM in a nutshell. The inverter's switches are doing that thousands, even tens of thousands of times per second to create the perfect illusion of an AC wave for the motor. The catch? Every single one of those flicks wastes a tiny bit of energy. And that wasted energy, which almost always turns into heat, comes in two main flavors. You've got conduction loss, which is just the heat you get from current flowing through a switch when it's on. And then you have switching loss, which is that little puff of energy you lose every single time you flick the switch. This creates the fundamental headache of inverter design. If you switch faster, you get a cleaner signal for the motor, but your switching losses go through the roof. If you push more current for more torque, your conduction losses absolutely skyrocket. It's a constant trade-off. And it gets so much more complicated. The inverter's digital brain isn't perfect. It has a finite resolution, kind of like a ruler where the markings are a little too far apart. These tiny errors can actually build up and cause weird vibrations or noise in the motor. Then engineers have to program in these microscopic safety pauses, called dead time, to prevent the whole thing from short-circuiting. But even that tiny delay can mess up the power delivery. And you have to make all of this work perfectly as the electronics go from freezing cold to boiling hot. It's a lot. So, we've managed to sculpt this beautiful, finely tuned AC power. Now it's time to actually make something move. Let's see how that electrical command turns into raw physical force. At its very core, an electric motor is a beautiful dance of magnetic fields.
The currents from the inverter create powerful electromagnets that push and pull against permanent magnets, and that's what makes the motor spin. The inverter's incredible precision is what gives you that instant, buttery smooth torque that EVs are so famous for. But the motor's own challenge is just trying to survive the immense heat this whole process generates, all while staying as efficient as possible.
Right, and here's a crucial point. The motor isn't working by itself. The gearbox is its essential partner. Let's say you change a gear ratio. That can multiply the motor's torque, which sounds awesome. But nothing in engineering is free. That mechanical choice immediately changes how hard the motor has to work, which then changes the electrical current the inverter has to supply, which affects the inverter's heat and efficiency. You see where this is going? It's all one big, deeply connected system.
So how on earth do you manage this crazy web of interconnected trade-offs? You can't just build a dozen multi-million-dollar prototypes and see what happens. No, in the modern world, you build it all in software first. You use these incredibly powerful simulation tools to predict the future. Engineers use something called a loss modeling framework. You can think of it as a super sophisticated calculator, almost like a crystal ball for heat. It takes all the performance data from the component suppliers, mashes it together with a model of the motor, and then it predicts exactly how much energy will be wasted as heat at any given speed and any given torque. And the workflow is just brilliantly logical. You start with the vehicle itself. How much does it weigh? How slippery is it through the air? From that, you can calculate the exact force needed at the wheels to get it moving. Then you work backwards through the gearbox and the motor to figure out exactly what the inverter has to supply. And once you know that, the model can tell you how much heat you'll generate before you've even ordered a single part. It's amazing. But here's the thing you have to understand, and this is the core philosophy of all engineering simulation. No model is a perfect crystal ball. The point isn't to get a number that's right to the third decimal place. The real goal is to compare your options. Is this new chip really better than the old one? What happens if we tweak the gear ratio by 5%? The model gives you the data to make smarter design decisions. Of course, these powerful tools are just filled with hidden traps. A simple typo in a unit can silently poison every single result, assuming a component's temperature is constant when, it's obviously changing all the time, or ignoring the subtle effects of those little safety pauses. Any one of these can lead you to a completely wrong conclusion. It takes a ton of discipline to get results you can actually trust. And all of that brings us right back to the central theme here. Engineering an EV powertrain isn't about finding one single, perfect, magical solution. It's about navigating a whole series of complex, interconnected compromises. So let's do a little pop quiz based on a real-world scenario. You're at a stoplight, it turns green, you floor it. The car is surging forward, you're getting pushed back in your seat, but the motor isn't actually spinning that fast yet. Why is this exact moment one of the most stressful for the entire powertrain? Well, the answer goes right back to those two types of losses we talked about. High torque demands ridiculously high electrical current, and when you push that much current through the inverter's switches, you generate a massive amount of heat just from pure electrical resistance. That's the conduction loss we mentioned. So even though the switches aren't flicking on and off as fast, the raw flood of current just completely dominates, making this a huge thermal challenge. And this right here, this slide brilliantly illustrates the central challenge the whole game. Let's say an engineer thinks, hey, I want to increase the inverter's switching speed. Okay, what's the pro? Well, you get a much smoother power delivery to the motor. That can reduce weird vibrations and maybe even get rid of that high-pitched whine you sometimes hear from EVs. But what's the con? Well, every extra switch costs energy, so your switching losses go up, which means more heat, and it probably means you need a faster, more expensive digital controller to keep up. It's one decision with pros and cons that ripple through the entire system. This balancing act, it never really ends. As we push towards brand new battery chemistries, exotic motor designs, and even faster silicon chips, the trade-offs, they don't go away. They just shift. They become new, even more complex puzzles. The next great leap forward in EV performance isn't going to come from some single magic bullet component. No, it's going to come from the engineers who can master this incredibly intricate dance and solve the next great balancing act.